All right, horizontal vibrating springs, looking at it from a dynamics point of view. Okay, so just like the last one, we're going to have some type of restoring force. So let's say we push this box back to this point, right? We squashed it up against this spring there. There's going to be its maximum restoring force at wherever I put it to, right? Wherever I put it there. Let's say I gave it some distance x. That's how far I placed it. Um, Now, if I want to figure out what the acceleration on that box or that block is, I can use two things. I can use Hooke's law in a combination with Newton's second law. So Newton's second law and Hooke's law. Mass equal to, or mass times acceleration, spring constant times our distance x. If you rearrange, and then you can figure out that a is equal to that. Okay, so it does have its maximum acceleration at that point. All the negative symbol here means is that if I give this thing a displacement in that direction, the acceleration and the force are going to be in that direction. If I gave it a displacement in that direction, then the force and the acceleration are going to be in that direction. So they're just always in opposite directions of each other, kind of like we've talked about before. All right, so one thing I want to, before I move on though, I just want to kind of go back to pendulums for a second. And so let's say you got this pendulum swinging back and forth, right? And I said, okay, what is the acceleration right when it crosses, our equilibrium position? So right there. And you might think, well, this thing as it's coming down, it's going to be going its fastest right there, right? We know it has its most kinetic energy right there. But right at that point, there's no restoring force, right? So it's got its biggest restoring force up here, right? It's got the biggest force that's pushing this thing back, pulling it. It gets smaller, 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 until right at that moment, it's zero. And then it switches directions when it's going the other way. So right at that point, the force is equal to zero. So the acceleration is also equal to zero at that point right there. That's going to become important. Nope. Because we're going to have a similar situation with our spring, right? So as this block is moving past our equilibrium position, the force and the acceleration are both going to be zero. It's going to be going its fastest at that point. V is the biggest, right? But force and acceleration are nothing. It doesn't need to apply a force anymore because it's at that equilibrium position. And then once it gets past that point, the force and the acceleration are going to start to point this direction. It's going to start to point the other way. That's going to be important for you guys to remember because that's going to come up quite a lot with any theory questions for this unit. So however you need to, remember that force and acceleration are both zero at the equilibrium point. Speed is the most, right? If we go down a little bit farther here now, so let's say now our block has gone as far as it will. So now you can see that force and acceleration are both pointed in the negative direction. They're both pointing back. They are their max at that point. They're as big as they're going to get. And what about velocity at that point? Well, it's come to a stop before it had to go back. So our velocity at that point is equal to zero. So just note that in this equation up here, I already went over that. Never mind. Confusing myself. Okay, so up in that, I talked about this already off the bat. So just like with the pendulum, though, acceleration isn't uniform, right? The acceleration and the force of this thing is always going to be changing. So this arrow up here would be getting smaller and smaller and smaller as it gets toward our equilibrium. So we cannot use our acceleration formulas that we used in kinematics. All right, example 3. So I'll let you guys look through this one. It's using just the setup that we had above, and you have to just rearrange and solve for x. Okay, now looking at horizontal vibrating springs from a energy perspective. So with a pendulum, we said that it was going to be made up of two types of energy, right? At any point on this thing, it's always going to be potential energy plus kinetic energy. And the potential energy was gravitational. The kinetic energy was, kinetic energy. We only have one formula for that. Now with a vibrating spring, we have our potential energy is now going to be spring potential. So we have to use a different formula. We have to use 1/2 kx squared. But then other than that, it's really similar. Our maximum kinetic energy will be as it crosses our equilibrium position. Our maximum potential energy will be where it's stretched out to one side or the other the most. So in this one, we can say, okay, I'll read it here first. A 0.4 kilogram mass vibrates at the end of a horizontal spring along a frictionless surface. If the spring's force constant is 55 newtons per meter and the maximum displacement, another name for that is amplitude, is 15 centimeters, what is the maximum speed of the mass as it passes through the equilibrium point? Okay, well, we have the spring constant and we have its maximum amplitude or displacement. So really with those two things, we can figure out what the maximum energy was, right? And we also are looking for the maximum speed, right? So if we just make kinetic energy equal to potential energy and max, right? Because they're going to be the same at different points. Then just fill in what you know. So 1/2 mv squared is equal to 1/2 kx squared. This time, though, we can't cancel our masses, right? That's the only kind of downfall with this one. So we do need the mass in the equation. And then rearrange and solve for v, and you get this. Okay, practice problems. I'll continue on the practice problems in another video. So I'm going to end this one here.